In this video, I'll go through some examples of two sample t-tests for independent samples. In the first example, we have two samples from two different bank branches, and the data represents checking account balances. And the sample size for the first sample is 28. And the mean is 1,025. And then the standard deviation, which we're going to estimate from each sample, in the first sample is 150. And then the comparable values in the second sample, 22 for the sample size, 910 for the sample mean, 125 the sample standard deviation. Here's the formula for the standard error, which essentially combines the two sample standard deviations using the sample sizes. Comes to 38.91. And then the t-statistic is the difference between the sample means divided by the standard error. We're testing whether the difference between the means is 0, so that's why there's a 0 in here. We can test for other numbers too, but 0 is the most common. Okay, we need a t-distribution here, as we're not assuming that the population standard deviations are known. And for the t-distribution, we need to come up with a degrees of freedom number. And one way to do that is to use this pretty horrendous formula. So, lots going on there. Essentially, it's going to come up with a number that is representative of both samples. So in this case, it comes up with 47 for the degrees of freedom. Anyway, once we have that, we can calculate the p-value. We'll do a two-tail test here. And so our p-value is the sum of the probabilities under the curve to the right of 2.95 and to the left of minus 2.95 for a t-distribution with 47 degrees of freedom. And this function here, t.dist.2t, will calculate that directly. So we just put in the test statistic and the degrees of freedom, and it calculates that two-tail p-value. In this case, it's below our significance level alpha, and so that allows us to reject the null hypothesis. There's evidence here that the two sample means are not the same. If we don't want it to do a critical value, make a decision using the critical value, then as usual, we need to find the value in the t-distribution so that we've got a tail area of 0.025 in the upper tail and 0.025 in the lower tail, as we're doing a two-tail test. And here's the Excel formula to calculate that. It comes to 2.012. And the decision is if that test statistic is either above 2.012 or below minus 2.012, then we reject the null hypothesis. And 2.95 is above 2.012. So it's in the rejection region, so we reject the null hypothesis. We could also calculate a confidence interval for the difference in the means. So the confidence level will be 95%, so we're doing alpha equal 0.05. The margin of error is the t-critical value times the standard error. And then the lower bound for the interval is the difference in the means minus that margin of error. And the upper bound is the difference in the means plus the margin of error, and comes to 37 and 193. So we're 95% confident that the difference in the population means is between 37 and 193. Let's see how Excel stat handles this. So do a parametric test, two-sample t-test. We'll select the data. Oh, looks like I already did that, so that's nice. Just check. Yeah, there we go. And then sample 2 is the other one from the other bank branch. 1 column per sample, column labels, students t-test. Okay, excellent. And then for options, we're doing a two-tail test, hypothesized difference of 0, and a significance level of 5%. And the population variances for the t-test, we're not assuming that they're equal. Okay, that is an assumption, a simplifying assumption that, amongst other things, makes the degrees of freedom calculation a lot easier, but we're not making that assumption here. So make sure this is not checked. And then we'll OK that. And we'll take a look at the results. Make sure we got the same as we did by hand. So 2.955 for the test statistic. Let's see if it's the same to the same number of decimal places yet, 2.955. 2.011 is our t critical value. It's actually just a little bit different here, and the reason is because when we did our degrees of freedom calculation, we rounded down up here, whereas Excel stat doesn't bother rounding down. It uses this exact degrees of freedom here. It's arguable whether that's really correct, because for t distributions they ought to have integer degrees of freedom, but anyway, that's what Excel stat has chosen to do. So it means that the critical value is a little bit different to what we calculated it to be. But then the p-value for the test, 0.005, and what did we get? Yeah, 0.005, same thing. And then let's see the confidence, and same decision, right? As the computed p-value is less than the significance level, 0.05, we should reject the null hypothesis. And then the confidence interval they got was, let's see, let's round that to the nearest whole number, 37 up to 193. And that's what we got to. Okay, let's do another example. So here we have, let's see, completion times for different softwares using current technology and new technology. And let's do the two-tail test first, just to illustrate. So sample size of 12 in the first sample, mean of 325, standard deviation of 40. Sample size of 12, mean of 286, standard deviation of 44 in the second sample. Standard error combines those standard deviations together using the sample sizes and comes up with a standard error of 17.16. Test statistic is the difference in the means divided by the standard error. Comes to 2.27. The p-value, actually we need the degrees of freedom for that, so let me just pull that over here. So we take a look at that before we look at the p-value. So here's that awful, awful formula again. Anyway, once you've got that programmed in, it's easy, right? Excel will do that horrible calculation for you. It comes to 21 in this case, and then the p-value, two-tailed test, so it's the sum of the areas in the two tails, comes to 0.034. Compare that with alpha, ask ourselves, is it smaller than alpha? Yes, it is, so reject the null hypothesis in favor of the alternative. Looks like there is a difference in the means here. Critical value, calculate that the usual way. So we're doing a two-tail test, so put half of the significance level in one tail, half in the other tail. So find the value of t for a t distribution with 21 degrees of freedom that will have 2.5% to the right. And that's the formula there for calculating that. Comes to 2.08, and two-tail test, so we're asking ourselves, does the t statistic either lie to the right of 2.08 or to the left of minus 2.08? It lies to the right of 2.08, so it's in the rejection region in the upper tail, and we reject the null hypothesis in favor of the alternative. Confidence interval is the margin of error, standard error times critical value. And here's the lower and upper bounds of that confidence interval. So we're 95% confident that the difference in the population means is between 3 and 75. Let's see what differences are if we were to do a upper tail test for this example. So everything up to here is the same. Data's the same, standard error calculations the same, test statistic calculations the same, degrees of freedom calculation is the same. The difference comes in with the p-value calculation, because now we're doing an upper tail test, okay, because we've got a greater than sign in the alternative hypothesis. So our p-value is going to be the upper tail area to the right of the test statistic. Okay, so it's half of what the two-tail p-value was. Decision criteria is the same. Reject the null if the p-value is less than the significance level. It is, so we reject the null. The critical value in this case is the value of a t-distribution with 21 degrees of freedom that would have 0.05 to the right of it. All we care about is the upper tail, because we're doing an upper tail test. So we put the whole of alpha in the upper tail, and the value of t that gives 0.05 in the upper tail is 1.721. Is that test statistic beyond 1.721 in the rejection region? Yes, it is. So reject the null hypothesis. Same outcome as doing the p-value method, and it will always be the same. Okay, let's see Excel stat do its thing on this data set. Two sample t-test. We'll select our data. Software test. There we go. And the other sample, software test, new. And all this is good. We'll do, actually, let's do the upper tail test here. Hypothesized difference of 0, significance level of 5%, and we're not going to assume equality for the variances, so off we go. And let's take a look at the results, see if we can match what we had with our hand calculations. 2.272 for the test statistic. Ooh, what did I do wrong? I looked at the wrong sheet. That's what I did. There we go. Let's get one more decimal place there. There we go, 2.272, yeah, bang on. 1.718 is our critical value. Remember, this is going to be a little different because it's using 21.8 for its degrees of freedom, whereas we used 21, we rounded down. So we got 1.721 for our critical value. They got 1.718, okay, close. P-value, 0.017. What did we get? Wrong sheet again. There we go, 0.017. So it's the same to 3 decimal places. Decision's the same. As the computed p-value is less than the significance level, we should reject the null hypothesis in favor of the alternative. Okay, it did do a confidence interval here, but it's not particularly meaningful because it's an upper tail test, and so the confidence interval goes all the way out to infinity on the right-hand side. So I'm not sure how useful that is. I think in general, confidence intervals tend to make the most sense for two-tailed, thinking about two tails. So that's why I haven't calculated a confidence interval up here. Okay, so that's two sample t-tests when we have independent samples.